Lectures 27 and 28, which will complete the discussion of wavelets, this idea, and especially in 28, their applications in signal processing, image processing. So this outlines the lecture as usual. I'm in continuous time today. So wavelets are functions. Up to now, we've been talking about vectors. Input signals was a sequence of samples, which it is in reality. And the key was the filters. Now, like maybe a fresh start with the idea of multi-resolution for functions. And that will lead us to the key functions, which are phi, the scaling function, and w, which is the wavelet. So that's our goal. But I'll be, like, as I say, a fresh start in continuous time. Before I start, could I just mention what I maybe haven't mentioned, the course webpage for the course 18, which is math number 085. Actually, it's a full year course, 18, 085, and 086, out of the Applied Math book. And then I should also mention the course number for the wavelets course, which probably doesn't start that way, so I won't try to get its course webpage right. But what I wanted to say was this page, which is maintained by whoever is teaching the course at that semester, and next fall it'll be me again, includes quite a few old exams. Now, I don't know who wants old exams, but everyone to his own taste, so there might be a high demand for old exams. And in case there is, I found an old exam that somebody else, friend of mine, had given when he taught the course, and he's a great teacher, and he particularly called my attention to the last two problems on his exam. So what I did this week was make copies of that last couple of problems on that final exam, just thinking you might like to take them home and have fun. I don't know the answers myself, so I'd be happy to with any discussion. Actually, those particular questions go back to calculus of variations. So that would be like review of a month ago. Here we are today with low-pass and high-pass filters, but now making a fresh start. Okay. So here's the idea then of multi-resolution. You know what I don't know, that's sort of a created word, I suppose, but it's a very in word that's seeing a function at different scales. And in a way that reflects what our ears do and what our eyes do and what our minds probably do. That is, if I look at a scene like this, I first of all take in the whole picture, but then I focus on a person and then on face and so on. We just we just change scales. Okay, so the idea in multi-resolution is that I have a space of functions, V0. So these will be spaces of functions. And I'll say what that means again. And let's call the first space V0. And then there's going to be a space, a bigger space, that contains V0. So V1, and then, of course, after that will come a V2, and so on. And that symbol means that this is like the coarser space, functions that are at the coarse scale. So this is coarse scale, finer scale, even finer scale, and so on. And the idea is that as we have finer and finer scales, we capture more and more of the function, so that sort of in the limit, we've got all functions. So the union of all these VJs would be the whole space, all functions that we're trying to capture, and in many applications, we have to. I haven't said what the whole space is, so I better do it. Usually, we're thinking about functions with finite energy. That's the space that's often called L2, finite energy. The energy, of course, is the integral of the function squared. Okay, should be finite. That's the famous Hilbert space. That it's the sort of appropriate infinite dimensional version of ordinary two-dimensional, three-dimensional, four-dimensional. As the dimension goes up, you have more and more components, and this is the space that has infinitely many components, but otherwise behaves like three-dimensional space. It's got angles, it's got dot products, it's got lengths, that's the length squared, so on. Anyway, it's the functions that we usually consider, and we're building up to those from this space V0. Okay, now, what's in V0? Okay, that's the key point. What's our space going to be? Our space is going to, V0, the basis is going to be, the basis meaning, let me not even use that word basis. Of course, space is going to be all combinations of, and that's what it, of a particular function. So this is like, this function is the key to everything. And I've used t as the variable, I could use x, and its shifts. So that's what's in the space V0. What's in the space V1? Well, you can guess. It'll be all combinations of what will be, you maybe just guess, and it's like good to anticipate because it connects then. What do you think if this is the finer space? We're looking at functions on a finer scale, and this is octave multi-resolution, so the powers of 2 come in. So the functions that give this space are the same phi, but with the finer scale shifted by 2, dilated by 2, refined by 2, whatever is the good verb. And the key is that refinement. Okay, so many papers about wavelets will begin with these assumptions that Mallah, I think, was the first to write down. So let me put his name up here, Stefan Mallah. They often, what I'm hoping to do is like save you the trouble of going through the assumptions. This is essentially what's going on. We have a sequence of more and more refined spaces, and we have a function with its translates that spans V0, and then scaled 2. Here the scale would be 4, then the scale would be 8t. It would be phi of 8t minus, and its shifts. And everybody recognizes if I look at phi of 2t, that squeezes the function by a factor of 2. Of course, the model problem, the easiest example is HAR, where phi of t is the box function. And then we said what's V0. We described V0 last time. If this is the box function on the interval 0, 1, I heard it described yesterday as the boxcar function, so maybe that's also a useful word. What's in V0? Take that function take all its shifts, integer shifts, take all their combinations, and what have you got? Step functions, right. Piecewise constant, so piecewise constant on unit intervals. On unit intervals. And now, let me ask about V1. So we drew those pictures, just constant on every interval, but a jump between. Okay, what about V1? Phi of 2, what's the graph of phi of 2t? It's, of course, the same thing, but only going to a half. And what's in the space V1 then? If I take all combinations of those guys and their shifts, that's what I meant, all combinations of this and all its half integer shifts, I'll again get piecewise constants, but the pieces will be half a unit long. So this is piecewise constant on can I say, half intervals. And you could imagine that. Then the next one would be piecewise constant on quarter intervals, and any smooth function, any function in our whole space, like whatever, like that, could get approximated first of all by something on unit intervals, and then I could do better on the half intervals, probably bring it down a little, stop that one there, and then I could do better on quarter intervals. Then I would approach, in the limit as the scale gets finer and finer, I'd get the function. Okay.
So are you restricting the values of k?
To be integers. Yeah, k should be integers. These are all integers. Minus infinity, or k equal 0, plus or minus 1, plus or minus 2, etc. Yeah. And I'm working on the whole line here. I'm not for my functions.
But then in your second, in V1, k can be 1/2 also, yes?
No, I think I always have to take a look. If I could write it as 2 times that, so you could say, yeah, then this could be 1/2. Right. Let me just draw phi of 2t minus 1, just to be so 2t minus k is what we're allowing. And let me draw phi of 2t, and below it, which I did, and below it let me draw phi of 2t minus 1. Where does that sit? Just so we see. When that 1 at first glance looks like we're shifting at a unit interval, but then because it's 2t minus 1, where does phi of 2t minus 1 sit? I'm claiming it sits right here, right next to it, that it's a shift of a half. Because you see, when t is a half, this thing will be 0 and the function will be starting. And when t is 1, this will be 1 and the function will be ending. So yeah, so that this dotted guy here is this guy. Yeah. So it comes out right. Yeah. Yes.
They're just finite combinations of those also?
Well, okay, that's a fine point, or a finite point. Yes. Maybe I should allow infinite combinations, but keep them with finite energy, so they tail off at infinity. It's yeah. It's of course our focus is sort of on a function on a finite interval, but if we want to be in these spaces and get all these functions on the whole line, then probably I better let there be infinitely many combinations, infinitely many terms in the combination. There was another. Yes.
Will it always be possible to express the second order one, the first order one, the lowest order one in terms of the next order?
You have hit on the central question. That's it. That's the key. So this looked a little innocent here. This saying V0 should be contained in V1, but it's the key to everything, because it means that this first guy, in particular phi of t, which is our champion member of V0, because all the others are just shifts of it, this first guy is also in V1. But the whole space is, so in particular our leading person is, phi of t is in V1. And now if it's in V1, it means it's supposed to be a combination of these guys. So that's the key. So that V0 in V1 leads immediately to the fact that phi of t is supposed to be in V1. And what's in V1? Combinations with some coefficients, and I'm going to call them h of k, of the basis functions for V1. And so that I'm jumping the gun, you could say, or leading the witness or whatever, by using the notation h for the coefficients. In fact, I'll go even further and call them h0 of k. So you have no doubt that there's the link between this setup of a bunch of spaces with a basis and the previous discussion of filters and particularly H0s. So the answer was definitely yes. That in this is, you could say, the classical wavelet framework. Now, in 2000, 2001, in the new century, there's you might find this somewhat restrictive. And you might be trying to create wavelets on spheres because you wanted to represent the geopotential as a combination of wavelets, or wavelets on surfaces because you work for Pixar and they're modeling, say, in Toy Story or other. I mean, that's become a big application now of computer-aided geometry and surfaces are involved. But that's like second generation. This is the place to start. And this is the equation to start with. This, it says that our function phi of t is a combination of phi of 2t minus k. And, of course, you saw it happen here. And the coefficients were 1 and 1. The coefficients, since the full box is which is somewhere here, is obviously 1 of this half box plus 1 of this half box, so the coefficients are 1 and 1 in that particular example. Of course, that's the easiest example. So this phi of 2t then, phi of t, I can erase it and put the equation, because we remember it's the box. Phi of t is then phi of 2t plus phi of 2t minus 1 in that example, our example. So the coefficients would be 1 and 1. Oh, and if we wanted to stick to our earlier convention that the coefficients add up to 1, well, 1 and 1 add up to 2, so I left space here to insert a 2 so that I could stay with my convention that the coefficients, low-pass coefficients, add to 1. That's a convention, and not everybody does that. Okay, so the beauty is that if we have a function which solves this equation with some numbers h0, that would be called, this is often called the refinement equation. This is the refinement equation, or the book calls it the dilation equation. So both words are in use. And that function, so most functions won't satisfy such an equation. Most functions suffice, well, oh, I think I left last time with the question of the hat function. Does it solve such an equation? And I think I probably implied with the way I said it that it did. So let's get that example up here too. The second case would be the hat function, which is on an interval of length 2, which suggests that I'm going to need 3 coefficients. You'll see that the number of coefficients matches the number of numbers 0, 1, and 2. So 3 coefficients, and I think I asked what they were. How could I express this hat? Let me blacken it, let me yellow it in. How could I express this hat as a combination of how much of a half of a hat shifted, and half of a hat shifted once more? Do you see what that I could get out of those 3 small hats? By combining them with the right coefficients, I could get the big hat. What would be the coefficients then? So for this one, this is then the hat example. The hat, phi of t, is what combination of small hats? 1, 2, 1. 1, 2, 1 is exactly right. 1 of this first guy, 2 of the second guy, which will reach up that far, and then 1 of the third. Right. And so if I wanted to take the 2 out, so I have phi of 2t, the hat, 2 phi of 2t minus 1, the middle hat, and phi of 2t minus 2, the right-hand hat. Those coefficients add to 4, so what do I do? I've got that factor 2 out there. So my coefficients, so my h naught, what's my h naught of k then for this one? Well, it's supposed to add to 1. I guess I can figure it out. It has to be 1/4, 1/2, 1/4, right? To be. So what am I doing? Am I doing something dumb here? No. Okay. It was 1 to 1 in proportion, but this was real. I only want what I drew there only had height 1/2, so I should have had a 1/2 there, and 1/2 there. That's the thing. That's the thing. And then when I take the factor 2 away, I'm down to 1/4, 1/2, 1/4. Good. Okay. But the main point is this, that I could consider this equation for other coefficients, and for those I'm not going to have any simple solution. If I take these coefficients, h naught of k, some other set of numbers, I'm not going to have a simple picture. And in fact, I may not even have a solution at all. So really, this has become the most important equation in wavelet theory. Is there a solution? So let me just put is there a solution? At all? Maybe I'll put at all. That would be a first question, not an easy question. Then would come a question, formula for it? How smooth is it? How many, now I have to mention a topic that's of importance. Which polynomials can it reproduce? It's approximation power. and I have to explain what that is. Questions that I want to know about my function and my space that comes from that function. So these are the questions. These are the questions. Is there a solution at all? What is it? How smooth is it? What good is it? That's really, and all answers have to come from these numbers, because all answers in terms of H naught of K. That's where we are. That's the posing the problem of the analysis problem for wavelets. And I haven't actually mentioned the word wavelet, so I'll mention that now in a moment. But just to repeat that this equation has constant coefficients. It's linear, but it's got two time scales, and that makes it so different from other equations that it didn't get studied for years, for centuries. Amazing. Yes? Could there be more than one solution? Right. Uniqueness. Right. Another question. It turns out that question, well, certainly if phi is a solution, so is 25 times phi, because we have that, so we would have to normalize it by, let's say, the integral of phi should be 1. That's the usual normalization. So we're normalized by the integral of phi dt equal 1 for convention. And then it is unique, effectively unique. And we'll have a formula for it. So in a way, that's our one way to prove uniqueness is to get a formula for it. It won't be the most explicit, simple formula in the world. And in fact, it won't be a formula that we would actually use to find the values of phi of t. Probably we wouldn't. And it won't be a formula that we'll find very convenient to answer these other questions, but it will be a formula for the solution. So that's like one direction, is to find a formula. So here are some of the answers. Here are some of the answers. Solution at all? And the answer is not always. Not by any means. And the formula? Well, the formula will be for the Fourier transform of phi. If we go into Fourier transform space, we got a better shot at this equation. If we go into the frequency domain, and it turns out to be an infinite product. So you can see why that's not the world's most convenient form to get a function.
By not always a solution,
So remember.
You've demonstrated a function that solves the equation.
You mean for a fixed h?
That's right. I remember. Okay. Now, so the input is now the h's. You give me some h's that add to 1. I say, okay, those h's add to 1. That's a low-pass filter. It's got a chance. Is there a solution with your h's? Now, why don't we just do an example? So, sorry? So, and I'll finish later that solution. But to come back to so this is the fun question in the subject. You give me some h's, and how do we decide if there is a solution at all? I mean a solution that's anywhere decent, like a solution that has finite energy. Let me tell you one case. So I'll now erase the outline because we're well into the lecture. Except I'm.
We want to start with h and derive phi, but it makes more sense to start with phi and find an h.
Well, most phis there won't be an h, because most functions. If you just give me a function phi If you happen to give me the hat function, I smile because, boy, I know the h. But if you give me some other function, or even the hat function on some, lopsided hat function or practically anything, there wouldn't be an h. So really, it's more this, it usually goes in this order. Well, I mean, it's like, but we want to know the answers to these questions. We want to know, here's what we ultimately want to know. What is a good H? What's a good filter to choose? And we would like it to be symmetric. That would be a good property to have. We would like it to produce a nice solution. In fact, we would like it to produce a reasonably smooth solution. We would like that solution to be useful, to have this approximating power. Because what do we plan to do with the function? We hope that, so here's what we hope. We hope that this space V0 captures quite successfully our signal. We're in continuous time now, so captures a typical signal. Of course, if it's a really difficult signal to capture, then we're going to need more of the details. But what we hope is that we hope to choose H0 so that we can say it in many ways. In continuous time, I could say I hope to choose H0 so that these give a really good approximation to my signal. They might be trying to match my signal. Well, actually, you're specifying the function phi raises a tricky question that's really never got resolved. Suppose we wanted to, the signal we're looking for is like a tank or something, shape of a tank. Okay, so you might say, well, match that. Choose phi to look like a tank. And then it'll be, then by using these functions as our basis, we'll capture a tank if it's there. But the shape of a tank, I have no idea what h's would give such a thing. So somehow that direction hasn't been very fruitful. We more likely ask what h's give good approximation to reasonable shapes. Good approximation to reasonable shapes. And then, fine, we say, great. So these are all good questions. I'm happy to have more. Yeah, Bob.
Is there some reason why it has to be a finite function? Why should
These h's or the function phi? Let's see. Well, first of all, if the h's are finite, the phi will automatically be finite. In fact, the length just matches. If I've got 3 h's, as I did in this example, the phi will go from 0 to 2. And that's a kind of first surprise about the solutions to this equation, that they do have finite length and then become 0. I mean, the solutions of differential equations, they go up exponentially or they decay exponentially, but they don't cut off. That's only possible because we have these 2 scales in here. So that somehow, so depending on the number of terms, so k will go from 0 to n, then our function will also go from 0 to n. That's pretty neat. So I guess then the answer, we don't have to stay with finite length. I mean, but that finite length functions corresponds to finite length filters and is sort of the natural starting place. Oh, but then I have, papers keep coming in of constructions that break out of this mold and say, well, let's use infinite length filters and have more freedom in the function. Yeah, it's and let me just mention one other example. Oh, I was going to mention two or three other examples. Okay, here's a challenge. Suppose I look at this particular dilation equation. Just that one. Okay. What's the filter that goes with it? What's the H naught? What are the coefficients that you're seeing on the right-hand side there? Well, there's only one coefficient, and it's 1. Right. And then that factor 2 is the 2 that I... Okay. So there is a lazy. That's called the lazy filter. It doesn't do anything at all. It just, it's the identity. Right? The matrix is the matrix of 1s on the diagonal. If I do the convolution, nothing happens. Now tell me what's the scaling function, because that's the right name for phi of t, is scaling function. I don't think I've written that down. Here, these are scaling. Not especially brilliant name, but anyway, name. Anybody know what function solves that? Delta equation does. Yeah, a delta equation does. Which was like news to me. So phi of t is delta of t. That's kind of fun. I never really thought about delta of 2t or something. And maybe we should think about this a minute. Why, whoever said delta of t, why, well, I won't ask how you came up with it, but let's just see that it's true. How do you, so we're claiming that delta of t is 2 delta of 2t, and I would like to know, what the heck does that mean? It's certainly clear that both sides are 0 away from the origin. Clear, totally clear. And it's clear that they both blow up at the origin somehow, whatever the delta thing means. But what does it mean? Why? How do I know there's a factor 2 in there? And what's going on?
You take a limit.
I could take limits. Yes. It has the same area. That's true. Yeah. Maybe that's the key insight, that if I integrate. Everybody knows that the integral of the delta function is 1. And then now suppose I integrate 2 delta of 2t. Do I really get 1 out of that integral? Change variables, right. New variable, let u be 2t. So u is 2t, and du is 2 dt. You see how that 2 paid off? Okay, and that's 1. So the areas are the same. So that's sort of why that factor 2 is in there. And more generally, since I'm into this somewhat direct question here, so the areas match of the two sides, but the full match would be to check that the only way you really know what a delta function is, because it isn't really a function, is that you know what it does to a smooth function. And what does it do to a smooth function? If you take a smooth function and you multiply by this Dirac, and you integrate, this is really the definition of the Dirac. And you get what? F of 0, right. Okay, so that's really the definition. I shouldn't, but I will put that. Okay, so that if this is the same, then we should check that it gives the same definition. So I should take f of t and multiply by this strange thing and integrate. And now, do I really get the same f of 0? Because then I would say, sure, they are the same. Why do I get, well, what am I going to do here? Same change of variables, right? Let 2t be u. The 2 dt is du. And, of course, t is u over 2. So, it looks a little different. But it's now I'm taking this function, I'm multiplying by delta, I'm integrating, and what do I get out of that? I again get this, I get the value of this thing at u equals 0, which is f of 0. Good deal. So the two sides gave me the right thing. Oh, okay. Well, so there is, I have successfully solved one more refinement equation, one more very, very special case. Shall we tackle another one? Let me tackle one more that I know the answer to. So I'll erase this for the delta. I'm going to write up a new special case here. Yeah. My coefficients are going to be 1, 4, 6, 4, 1, all over 16 to add up to 1. So I don't have delta anymore. It's phi of t. So I'm okay if I erase this example and make space for the new one. All right, then this is the next example. So the coefficients are 1, 4, 6, 4, 1, which is really, it's the convolution of 1, 2, 1 with itself. Well, 1, 2, 1 over 4, I guess it was. The convolution of 1, 2, 1 with 1, 2, 1 would be 1, 4, 6, 4, 1. How do I know that? Well, I'm multiplying polynomials with coefficient 1, 2, 1, squaring it, because this one has the same 1, 2, 1, and then, you know, if I remember those binomial numbers or Pascal's triangle or something, I'm seeing those numbers. So phi of t, then, it turns out that if I look at the equations, it would be the convolution of the hat with a hat. If I know the solution for that and the solution for that, then if I convolve the coefficients, you could just check that I convolve the solution. So what is the hat convolved with a hat? First of all, tell me how far it stretches. How far does the hat convolved with a hat stretch? Remember the hat, we've already got up here, it stretches from 0 to 2. Now where will hat, if I convolve that with itself, it'll go to 4. Right, it'll go to 4. 0, 1, 2, 3, and 4. And any idea what it will look like? Now, let me just say, doing a convolution in your head is not a lot of fun, especially when the function has different parts, and you would have to, in the convolution integral, you'd have to keep track of which part you were in. And actually, it's going to produce 4 different parts here. Well, let me say what it is. It's the cubic spline. It's the cubic spline. But why? We ought to think for a bit. But it's the spline. It goes, and then it changes to some other cubic, and then it changes to some other cubic, and then changes to some other cubic, and it's otherwise 0. And this fact that it has finite length is pretty neat. Again, yeah. So that's a very important function, and of course was discussed long before the word wavelet ever got thought of. And nobody paid any special attention or even probably noticed that that function solved one of these refinement equations with nice numbers. But now, of course, we do notice that we think, hey, yes, the spline is a solution to this equation with this very special, important low-pass filter. So there's another example. So there's a family of examples, in other words. Box, hat, quadratic spline, cubic spline, on up, that we can do exactly. And that is about the limit of exact solutions I know. Yes, Les?
I understand that the H's were a convolution, which is pretty simple. Why does that mean that the C's are
Well, I just waved my hand and said that will work. I would have to erase and make space just to do that. But I leave that as an exercise. This is a professor's privilege, right? So suppose I have one low-pass filter, and and the function phi of t that corresponds. And then just to make the exercise simple, I'll keep the same coefficients, giving the same function, and then I'll ask, what about the coefficients that come from convolution of this? And my claim is that the result would come from convolution of the phi with itself. So I'm not answering your question. I'm asking it back to you, which is no, symmetry isn't built into this at all. Well, it's built into these examples, but I'm not making any assumption about symmetry here.
Convolution property is true for any, even non-symmetrical vectors?
That's right. That's right. And maybe I'll give a way you might tackle the proof. First, you could, I'm pretty sure you could do the proof directly in the time domain. But probably, for convolution, you're better off to get in the other domain, right? Do it in frequency domain where it's a multiplication. So let's just see how I would get into frequency domain. Yeah, okay, good thinking. All right. So I could finish this formula, which would be the formula in the frequency domain. Okay, so let me finish it. This is an infinite product. Well, who needs infinite products? But that's what it is. I'm in the frequency domain, so you will not be surprised to see the function that we called capital H of omega appear. Right? You remember what capital H of omega was? It was the function of omega, which had these as its coefficients. So capital H of omega, you remember, was the sum of the coefficients times e to the minus j. You see, I'm using j today. J omega k. The finite series, it's just a polynomial because we assumed we're thinking here of FIR filters. You remember that H of omega? Now, H of omega, the thing is, when I go into the frequency domain, I've got two frequency scales. If the Fourier transform of this gives me phi hat of omega, the Fourier transform of this will involve phi hat of what? Anybody know? It won't be 2 omega, because somehow it flips the other way around and it will be phi hat of omega over 2. Yeah. Yeah, and we could patiently do that. And of course the book does it. And so omega over 2, and then okay, let me say it in words without writing it down, but I'm willing to write it down. When I take the Fourier transform, I'll write down. Yes, sure. I'll write down what the Fourier transform is of that equation. The Fourier transform of this equation is fantastic. I'll put it in yellow to highlight it. So I'm taking the Fourier transform. So I get phi hat of omega on the left. And what I get on the right, which is I'll just write down the neat answer. It's h, this very h at omega over 2, phi hat of omega over 2. And the factor 2 disappears also. Isn't that neat? That in the transform domain, well, this was a convolution, right? This was really a convolution followed by a change of scale. And of course, in the frequency domain, it becomes a multiplication with a change of scale. Change in the opposite direction. If it was 2t there, it'll be omega over 2 here. I really recommend that. Here's a serious suggested exercise, is to take the Fourier, it's just terrific practice, to take the Fourier transform of that and see that you get that. So do you see that phi hat of omega, every time we, then let's take one more step. This would be h of omega over 2. Now what could I substitute for phi hat of omega over 2? using the same, just recursively, it would be h of omega over 4 times phi hat of omega over 4, right? Let me pause a second because it's so neat that that works so nice in the frequency domain. But it's nice, but it's not like self-evident because there's still this change of scale. And then, of course, I carry on, and then I get an h of omega over 2 times h of omega over 4 times h of omega over 8. And you can see that in the limit, I'm getting this h of omega over 2 to the j. That's my formula.
What happened to the,
Oh, what happened to this guy at the tail end? Okay, it was, yeah, good question. So it goes away some. It goes to 1. Why does it go to 1? Yeah, so there should be a phi of omega over 2. So I'm claiming that this guy, no, it goes to phi hat at 0, right? Because I keep dividing by 2. This is approaching that factor that's on the tail end. So once I've got about 77 terms in that product, I've got phi over 2 to the 77th, and it's phi of omega over 2 to the 77th. So it's very near phi hat of 0, and that's 1.
but because your function is being squeezed more and more,
Yes.
and its integral staying the same, it must be something a little more like a delta function.
I don't think so, but I don't know quite why not.
Because the amplitude doesn't go up.
Yeah, maybe it's because we're in the frequency domain.
The area is not constant.
It's not.
It bears checking, of course.
If it's not, then transform is
So let's see.
going to be good.
First of all, why is phi hat of 0 1? Because, well, that's the same as our little convention here. That's phi hat of.
That's the integral.
That's the integral, right?
Is 1. So it's got to be going up.
So somewhere in here, let's see. I know it does approach 1, but I don't know the right explanation to give here. We're at phi hat. So this is, if I take j terms here, then I have going along and stopping at 2 to the j eventually, then this would be phi hat of omega. For each omega, yeah, for each omega, this will approach phi hat of 0. So maybe this is the point, that this gives us an answer, a good answer for each omega. Well, a good answer in this, so we get an infinite product. Well, that's not the world's easiest answer. And then if we wanted to ask the question, what's phi? Then I'd have an inverse Fourier transform still to do, and be lucky to be able to do that. So you can see that it's extremely lucky to get to have an explicit solution. Not going to happen often. And maybe what led us to the question is, this form would give you a way to tackle my little convolution question. You remember what was the question that we started with? That if I had the phi, which solves this equation, then now if I convolve h naught with itself and I look at that equation, I'm claiming that the answer would be phi convolved with itself. Well, and why? Because in this domain, in the frequency domain, when I convolve this with itself, what would it do to capital H? It would multiply it by itself, right? So then that would be, then I'd have h squared, and I'd have phi hat times phi hat. So I'd have phi hat squared in the frequency domain, and when I go back, I'd have phi convolved with itself. It's the convolution rule that's coming up there. But this is a little bit tangential to the central, well, no, it isn't really, because what we discover is we got an answer here at each omega. So why do I say the solution is in doubt? Why do I say not always when I've produced the answer? And it does, this product does converge at for each omega. Because the H is, if this is a low-pass filter, so I really need to build in this fact that the sum of the H naught of K's is 1. That's also part of my convention. Then these things approach 1, and the product converges. But, so can I ask again? I got an answer. Why should I say there isn't always an answer?
So maybe that it converges differently for each omega, so you can't really create a...
That's right. I got an answer for each omega, but now if I want to go back and find the function, well, by the way, what was the answer for the lazy filter? What was phi hat of omega for what was capital H for the lazy filter? Remember, the lazy filter just had one coefficient, which was 1? It's a constant. In fact, it's 1. So I have a product of 1s. So I get the answer 1, which is exactly right? Phi hat of omega should be 1 when phi is the delta function. So that very lazy case, that's the lazy lecturer too, to check that case. Okay. But no, the main point is, you give me a function of omega here, or we've discovered one, but that's by no means sure that we can invert that and get anything decent as a function of t. And what is the requirement, or what would be a? When would I know that? Yes, I could invert it and get a decent phi of t. I mean, what kind of property of phi hat tells me yes, there is an inverse and a decent function? So if phi hat is identically 1, there isn't a decent function. It's the delta function. If phi hat is a sinc function, then there is a phi, and what is it? It's the box. What's up there? Yeah, I mean, why is a sinc function fine? I can invert that and get a box, where the constant function, if I invert that, I get a delta, which is not an okay function. And then all sorts of in between. I mean, of course, everything's in between. So let me ask that question again. What sort of Fourier transforms do good functions have? So that I say, yes, I can. That comes from a good function, and there is a solution. Well, those would be really good. If phi hat of omega is band limited, as for the like the one that gives me back the box function, great. Otherwise, sorry, no. What is it? I'm not saying the right thing, am I? Or am I? Yes. Let me give my answer. This function, if it comes from a good function, it should decay. It should tail off. I mean, it can wobble a while, but I would like it to tail off. And of course, the bad one is the constant function that doesn't tail off. That leads to delta, which is off the chart. The band limited one not only decays but actually dies. Of course, so that leads to That leads to very good functions. But Gaussian, what would the Gaussian lead to? A Gaussian, right. So still maybe if that's sensationally good, and the Gaussian should qualify as very good, and lots of others. So others, anyway, you see what I'm saying. Okay, but my point is, again, we've got an answer for each omega, but we haven't got a very good way to tell, do those answers decay as omega gets large so that I can do the inverse transform and find a nice phi? Let me give an example where we won't have a nice phi. Yeah. Well, no, it is the solution, but I wouldn't say, yeah. It wouldn't be a legal. It's not a solution I'm proud of. Right. Yes, that's right. That's right. So the solutions that I can work with are and use. I want their combinations. You give me combinations of the delta function. Well, boy, I want things like hat functions and splines and I'm willing to accept a few wiggles, but I don't want infinities. Yeah. So the delta function would be a case. That would be an example. I would say there is no solution in my sort of standard finite energy space. Well, it's pretty hard to decide. So I guess what I'm trying to say is some H's give a solution in my finite energy space, others don't. Let me take one that surely doesn't, because it's just sort of fun to play with these things a little. Suppose I take here you go. Suppose I take this equation, phi of t. Now I'm going to get the coefficients to add to 2. So suppose I took 3 phi of 2t minus 1 phi of 2t minus 1. I claim that choice, so I guess my filter h then is what? H naught here is 3 halves and minus a half, and they add to 1 and looks, sort of half okay. What would the graph of capital H look like for this case? Let's see, what is capital H? H is 3 halves of 1 minus a half of e to the minus j omega, right? I'm just like, I'm going to claim that this is a bad guy. But just to see, first of all, it does go through the point 1, so it's like, it's okay to consider it anyway. But then, what does it do? Well, I guess at pi, it's no good. So that I really know that this example is in serious trouble. Because what is it at pi? At omega equal pi, this will be minus 1, so it'll be, is it 2 at pi? Is that what's happening here? It doesn't go to 0 at pi. At omega equal pi, this is minus 1, so I think it's 2, is it? Is it a graph like that? Well, gosh, that's in serious trouble. And now, how do I, coming back to the equation, how do I see that I'm somehow, it should be supported on the interval 0 to 1, because I've got 2 coefficients, and it is. And it's not a delta function, but it's almost as scary. I mean, somehow, I don't know exactly, yeah.
Your infinite product.
Oh, okay. Go with the infinite product.
If it gets bigger than 1,
Yeah, right.
then
Right.
go out.
At least You're right. I could try to go with that infinite product, and it would converge. It would for each omega. For each omega, this will converge, because there's an omega over 2 to the j here, and that gives us something good at each omega. But if I graph that, I have no idea, none. If I graph this thing, because of course I can't take an infinite product in my head, to put it mildly. But so here's my h of omega, here's my formula. Actually, if somebody's got a computer handy that's sitting idle, that would be an idea to go with it. Just graph this thing for different omegas. It'll be complex, admittedly, but let's not, that's okay. We've got a real and imaginary part. What do you think would happen? Or took the log. That seems like a smart idea. Then I've got to take the log of this guy. So, all right, whatever the computer is happy with. I don't think it'll be as bad as a delta, I guess. So I think that the h of that this phi hat of omega I don't expect it to approach a constant. But then nor do I expect it to decay. I don't know what it does. Maybe it bounces around. Anyway, there's no decent function phi of t. How you could still ask why do I think that? Well, partly I think it from that. Yeah, maybe I should look at particular values of omega, like omega equal multiples of pi. I might learn something, actually. That might be a smart thing to do. Let omega be multiples of pi, and then oh, no, it would still be pi over fractions there. Not too good. Well, but somebody is observing that all the factors would be above 1? Oh, yes, you're right. Sorry. Shall I just say that again, which you realized before me? That h has magnitude bigger than 1, apparently. So apparently phi hat has magnitude bigger than 1. So which makes it look as if it be, because it's a product of things bigger than 1. So, but converging to 1. Well, that's interesting, isn't it? Let's see. Better. Oh, sorry, the factors converge to 1. Yeah, the factors converge to 1. Let's see. Would we be able, here, you want a little practice on infinite products? Okay. What's the infinite product of just the numbers 1 plus omega over 2 to the j? I don't know. I figure we ought to be able to do that, but I'm not sure. There's another exercise. Figure out that infinite product. So that's 1 plus omega over 2 times 1 plus omega over 4 times 1 plus omega over 8, and so forth. My point was that every factor is bigger than 1, but the product is still finite. Because
you put an amplitude phase on that. The amplitude, you just make that some amplitude times e to the j omega psi, something like that. Each of those.
you're going to make me...
Write that as a complex.
Okay, this times some e to the...
Well, no, an amplitude. The amplitude is greater than 1.
Okay, I'll let that be the amplitude. I don't know if it's okay. Now we're out of time here, but let's see. If I just took this thing as it stands without doctoring it, this is like practice on infinite products, which we're all, of course, highly familiar with, infinite products. I realized that I hadn't seen an infinite product since graduate school. And when I saw it there, it was only one day, and I thought, luckily I'll never see these again. And here they are. But I believe that infinite product, and let's make omega be 1. Hey, why should we struggle here? What's the product of 1 of if I multiply 3/2 by 5/4 by 9/8 and so forth, do I get a finite number in the end? All those factors are bigger than 1, but they're approaching 1. That's what I meant to say. I think I do.
Yeah, do use Fourier to take the log of it, and then
If I take the log, then
the small approximation to the log.
right. That's right. That's a good point. Yeah. The good way to analyze infinite products is take the log. Good point. And then we have an infinite sum, and we know about those. Right. Yeah. So this converges to some limit that. Let's see. If I actually multiplied these things out, well, yeah. I mean, why are we doing this? But if I took this, it would be 1 plus 1/4 plus 1/2 plus 1/8. Look at the beauty of that. Right? When I just take this product. And now if I multiply by 1 plus 1/8, what do I have? If I take all the terms. Well, I've got a lot of terms. I'm feeling it might be 2. I don't know. Not 2? Yeah. I'm not. Anyway, back to this crazy example. Somehow it looks to me like all the factors are larger than 1, but they're approaching 1, so that the infinite product will converge and will give us some function, and that function will be bigger than 1, maybe not bigger than 2, or not bigger than something, and it'll wander around, and it'll be a bad function. It won't be a function. This would be a case of the not a solution. It wouldn't have finite energy. How do I know it wouldn't have finite energy? I promise to stop with that question. Suppose I know, which I do, that phi hat of omega is somewhere between 1 and, let's say, k. How do I know that the energy is not, that when I take the inverse transform to get my phi itself, how do I know that it hasn't got finite energy? So let me write that down again. So I think we would learn from this that phi hat, or its magnitude, was somewhere between 1 and some number that would come from some number k. And I claim that we know we're in trouble. That if I have a Fourier transform that's in this range, I know the energy isn't finite in the function, so I know I have not got a finite energy solution. And why is that? Yeah, what's the relation between energy in a function and energy in the transform? They're the same. They're the same, right. So the one thing I do remember is that the integral of the function squared is always the integral of its transform squared, with maybe a 2 pi or something. Okay, and what's happening here with this? If my function never even goes below 1, it hasn't got a chance. It hasn't got a chance in heck of being finite, so it's infinite. And so then I know the energy in the function is infinite, and it would be a case with no solution. And I could try to figure out that function, and I would see it blew off to infinity at certain points. Maybe not at all points. That's the beauty of these functions, of these phis, the phi that solves the equation. It'll blow up probably at a whole lot of points, a whole dense set of points. It might not blow up at other points. It's just quite remarkable what this equation leads us to. So my point here ending this lecture is that a very simple choice, 3/2 minus a half, can lead us to a totally strange function. But, of course, that's not what subject is about. So can I, in lecture 28, come back to sensible functions, sensible filters, where there is a solution, and ask about how good it is, how smooth it is, how good it is in approximation and in applications, and then move ahead to the applications. So luckily we're a lecture ahead of schedule, but I do want to today to not just work with this equation, and I still have to tell you about wavelets. This, I've given you the phi but not the W, so that's coming in the next lecture. So could we start the next lecture at 3? It's 3:20 now. 10 minutes or 15 minutes maybe 15 minutes. 3:35.